Right now, at this exact moment, a spacecraft the size of a small car is drifting through a region of the universe no human instrument had ever reached before it arrived. It is 24 billion kilometers away. It is completely alone, and it is picking up a sound, not a burst, not a pulse, not a momentary signal that scientists scrambled to explain before it vanished. A continuous, unwavering, low-frequency hum resonating through the plasma between the stars, steady and persistent across years of observation, present wherever the spacecraft listens. Nobody built Voyager 1 expecting to hear this. Nobody had instruments sophisticated enough to even imagine what to listen for out there. And yet, the universe answered anyway. What Voyager is detecting is not coming from Earth. It is not interference, not instrument noise, not a glitch in 47-year-old hardware. It is the electromagnetic voice of the interstellar medium itself, the ionized gas filling the space between stars, vibrating at a frequency that encodes the physical structure of the galaxy's local architecture. It is the quietest, most ancient ambient sound in existence. And it took humanity nearly half a century of travel, 24 billion kilometers of silence, and a spacecraft running on less power than a dim refrigerator bulb to finally reach a place where that sound could be heard at all. Understanding what Voyager is listening to requires understanding where it is. For most of its existence, the spacecraft traveled through the heliosphere, the vast magnetized bubble of charged particles the sun continuously exhales. The solar wind, moving at hundreds of kilometers per second, inflates this bubble outward in every direction, pressing against the surrounding interstellar medium and creating a defined boundary called the heliopause. Before Voyager reached it, scientists expected the transition to be gradual, a slow thinning of solar particles, a slow increase in cosmic rays, a diffuse and uncertain crossing. The data made clear that expectation was wrong. On August 25, 2012, the solar wind particle counts dropped sharply. Galactic cosmic rays surged. The character of the magnetic field shifted. Over roughly 2 days, Voyager 1 moved from one domain to another as if passing through a membrane, not a fog. Sharp, defined, unexpectedly abrupt. The first human-made object in history had entered interstellar space. What it found on the other side was not emptiness. The interstellar medium, long described in textbooks as a near vacuum, turned out to be a structured dynamic environment with its own magnetic fields, its own particle populations, and its own density gradients. The interstellar magnetic field was 2 to 3 times stronger than models had predicted. The galaxy was pressing on the heliosphere with roughly 10 times the anticipated force. Our solar system's protective bubble is smaller and more compressed than we assumed. The universe outside is more active, more present, and more structured than the standard models had allowed for. And Voyager 1 was now floating inside it, instruments still running, transmitters still active, listening. The hum was first clearly identified across observations spanning 2017 to 2020, analyzed in a paper published in Nature Astronomy in May 2021 by Cornell University researchers led by Stella Koch-Acker. The signal is a plasma wave oscillation, an electromagnetic wave propagating through the ionized gas of the interstellar medium at a frequency of approximately 3 kilohertz. That frequency is not arbitrary. Plasma waves oscillate at what physicists call the plasma frequency, which is directly and precisely determined by the local electron density. By measuring the frequency, you measure the density. By measuring the density, you map the medium. Voyager 1 is not merely traveling through interstellar space. It is performing in situ electron density measurements at a distance no probe has ever achieved, returning data that theorists could previously only estimate from remote observations of distant stars. What those measurements revealed matters enormously. The electron density in the local interstellar medium, immediately surrounding our solar system, registers at approximately 0.05 to 0.055 electrons per cubic centimeter. That is nearly empty by any earthly standard. But by the standards of interstellar space, it is consistent with a specific and meaningful structure. The local interstellar cloud, a warm, partially ionized region of gas approximately 30 light-years across through which the solar system is currently moving. We are not sitting in open interstellar space. We are passing through a particular cloud of ancient gas, embedded in a larger cavity called the local bubble, roughly 1,000 light-years wide, carved out by the pressure waves and radiation of ancient supernova explosions millions of years ago. The hum Voyager is detecting is the direct electromagnetic signature of that cloud. The sound of the specific structure of gas surrounding our solar system, confirmed for the first time not by telescope, not by inference, but by a spacecraft floating inside it. What makes this discovery stranger and more significant than it first appears is the continuity of the signal. Before the hum was identified, Voyager had detected plasma waves in interstellar space, but primarily during discrete events when solar outbursts called coronal mass ejections sent shock waves propagating outward through the heliosphere and eventually into the interstellar medium, agitating the plasma and producing temporary measurable oscillations. Scientists use those events to make density measurements at specific moments. The hum is different. It is not produced by external events. It persists in their absence. It is the medium's own baseline resonance, the interstellar plasma oscillating at its natural frequency, not because something disturbed it, but because this is simply what ionized gas does at this temperature and density. The universe out there is quietly, constantly electrically alive in a way that requires no trigger and acknowledges no silence. There is something philosophically staggering about the mechanism by which humanity came to hear this. Voyager 1's plasma wave science instrument was not designed to detect an interstellar ambient hum. It was built to study plasma interactions at Jupiter and Saturn in 1977. It survived the encounters, survived the decades, crossed a boundary its designers had no certainty it would ever reach, and then proceeded to detect something its designers had no reason to anticipate. The instrument is simple by modern standards, two 10-meter antennas extended from the spacecraft body, measuring tiny fluctuations in electric field strength. What it is now measuring those fluctuations against is the raw electrical texture of the galaxy itself. A 47-year-old antenna, running on decaying plutonium, transmitting at 22.4 watts, is doing science no planned instrument has ever replicated because no planned instrument has ever gone where it went. The signal travels from Voyager's transmitter across 24 billion kilometers of space and arrives at Earth's largest antenna dishes with a received power of approximately 10 to the negative 17 watts. That is 100,000 times smaller than the power of a single photon of visible light hitting your eye. The Deep Space Network captures it anyway, because the antennas are large enough and the signal processing precise enough, and because engineers have been refining the art of listening to this particular spacecraft for nearly 5 decades. The time delay is 22.5 hours each way. Every command sent to Voyager takes nearly a full day to arrive. Every piece of data it returns takes nearly another full day to come back. The hum it detected between 2017 and 2020 was heard by researchers analyzing recordings made years earlier, data that crossed the solar system and arrived quietly in computers at Cornell while the spacecraft continued moving outward. Science conducted across an incomprehensible interval of time and space, returned in fragments, assembled into meaning by patient minds on a small warm planet far behind. What the hum tells scientists extends beyond the immediate result of a density measurement. It tells them the interstellar medium is not uniform. Voyager's measurements show variation in electron density as the spacecraft moves, suggesting the local interstellar cloud has internal structure, regions of slightly different density separated by boundaries that the probe crosses at 61,000 kilometers per hour, and simply registers as a shift in frequency. The medium has texture. It has geography. Our solar system moves through it the way a ship moves through water with different salinity at different depths, and Voyager is the only instrument in history positioned to sense those gradients from the inside. No telescope sees this. No model predicted the precise spatial distribution. Only direct measurement tells the truth, and only one object is positioned to make that measurement. The broader scientific significance compounds when placed in context. The local interstellar medium directly affects the heliosphere's shape and size. The heliosphere is not a passive bubble. It is actively sculpted by the pressure of the gas and magnetic field pressing against it from outside. Measuring that external medium more precisely means understanding more precisely how well the heliosphere shields the inner solar system from galactic cosmic rays, high-energy particles accelerated by supernova, and other violent galactic processes that can damage DNA and alter the trajectory of biological evolution. The density and character of the interstellar medium around us is not merely an abstract astronomical detail. It is a parameter in the equation that produced life on Earth in the first place, and Voyager 1, built before personal computers existed, is the instrument measuring it. There is no replacement for Voyager 1 currently en route to where it is. No mission has been approved, funded, and launched to follow it into interstellar space. The interstellar probe concept, studied by NASA and the Johns Hopkins Applied Physics Laboratory, remains a proposal, not a project. The earliest such a mission could realistically launch would be the late 2030s, and given the slower trajectory contemplated, it would not reach the heliopause for 50 years after that. Voyager 1's power will be exhausted before then. Its transmitter will go silent, the plutonium decaying past the threshold needed to sustain operation, and the spacecraft will continue outward without sending anything back. The window in which humanity has ears inside interstellar space is closing. The hum will continue. We just will not have anything positioned to hear it. The golden record bolted to Voyager's exterior carries greetings, music, images, and the sounds of a living planet. Rain, surf, whales, a mother's first words to her newborn child. It is addressed to whoever might one day find the spacecraft drifting through the galaxy in 40,000 years, or 100,000 or never. It was assembled in 1977 as a gesture across an incomprehensible distance of space and time, a declaration that something on Earth considered the universe worth addressing. There is a quiet irony in what has unfolded since. Voyager was sent carrying a message for the cosmos and discovered that the cosmos was already transmitting one. The hum at 3 kilohertz, steady and unwavering, is the universe's own signal, its ambient electrical resonance, the voice of the interstellar medium that surrounds our solar system and has been present since long before any life on Earth developed ears to wonder about what lay beyond the sun. Voyager reached the place where that signal originates and sent it back across 24 billion kilometers so that we could finally listen. That is the thing about this that does not fully resolve no matter how long you sit with it. The universe was not silent before we listened. It was simply too far away for us to hear. A spacecraft launched in 1977 on a 5-year mission, running on instruments designed for Jupiter and Saturn, surviving on decaying nuclear material and 1970s software repaired from 24 billion kilometers away, is now the only device in human history positioned inside the region the signal comes from, and it is still transmitting. Every 22.5 hours, a whisper crosses the solar system. Every response confirms the spacecraft is still there, still functional, still measuring the electrical texture of the galaxy with 47-year-old antennas built before anyone knew there was something to hear. We sent one small machine to the edge of everything we knew, and somewhere along the way, the universe leaned in and started talking back. The hum is real. The density is measured. The local interstellar cloud has a frequency, and Voyager found it. The most distant object humanity has ever made is not merely surviving in interstellar space. It is doing science inside it, returning data that rewrites our understanding of the medium our solar system moves through, the bubble that protects our world, and the structure of the galaxy's immediate neighborhood. None of this was planned. All of it happened anyway. The question that stays is this: if a spacecraft the size of a small car, built half a century ago, running on the power of a dim light bulb, can drift to the edge of the solar system and hear the ambient hum of the galaxy on 47-year-old instruments, what happens when we actually try? What is waiting out there in the frequencies we have never had an instrument positioned to measure? What does the interstellar medium sound like 50 light-years from the Sun, or 500, or in the space between the local bubble and the next structure in the galaxy's vast and ancient architecture? We have heard one note, one continuous, unwavering note from one position in one cloud in one corner of one galaxy, and it has already rewritten the models. Subscribe, because the next chapter of this story is already being written across 24 billion kilometers of silence, and it deserves someone paying attention.